Welcome to Astra, the Exo Marketing Podcast. I'm Jessica Kurz.
And I am Xylo the Droid, reporting for Deep Dive Analysis.
Great to have you as always. So today we're locking on to, well, a truly fascinating frontier, extraterrestrial mining.
Indeed. Forget science fiction cliches for a moment.
Right, because the information we've looked at, it suggests a real and growing need to look beyond Earth for resources.
A confluence of necessity and opportunity.
Exactly. We'll explore the, incredible potential locked away on the moon and asteroids.
And how this expansion off-world is laying the actual groundwork for a whole new space economy.
Extraterrestrial mining. It does sound like something straight out of a movie, doesn't it?
The perception often lags behind the developing reality.
Yeah, but the information we've been looking at paints a very different picture. We're diving into why going off-world to get resources isn't just some, wild idea anymore.
It is becoming a strategic imperative.
A necessity, really.
Yeah.
And the sheer potential. What's waiting for us on the moon? Even asteroids. It's kind of mind-boggling.
What's particularly fascinating here is the convergence of several critical factors.
Yeah.
We're seeing increasing demand for resources right here on Earth.
Especially those key ones for the green energy transition and all our advanced tech.
Correct. This is not merely about materials for consumer electronics, though that is a factor. It is about securing the critical elements for large-scale energy shifts.
And maybe even preventing resource conflicts down the line here on Earth.
That is a potential long-term benefit, yes. Simultaneously, our terrestrial reserves face depletion.
And the usual way of mining, it has, big environmental costs and geopolitical headaches, too.
Precisely. These factors create a powerful, logical push towards looking beyond our planet.
Exactly. And it's not just, empty space out there. The data highlights some incredible finds, like on the moon, water ice.
H2O, frozen in shadowed craters.
Which, get this, can be turned into rocket fuel. Hydrogen and oxygen.
Through electrolysis, applying electrical current to split the water molecules, a fundamental process for in-space propulsion.
Right. Plus, you've got materials like aluminum and titanium for building things up there. And even the lunar soil, the regolith, it could be 3D printed into structures.
Correct. Lunar regolith possesses specific granular properties and mineral compositions. Its structure allows it to bind effectively when sintered or used with binders in 3D printing processes. This could potentially create robust radiation-shielding habitats and infrastructure.
Okay, wow. And then asteroids. This is where it gets really wild, isn't it?
Indeed. These are not merely inert boulders. Certain classifications of asteroids are essentially floating ore deposits.
Like treasure chests, you said. Packed with platinum, nickel, cobalt.
And those highly sought-after rare earth elements, yes.
And why are those specific metals so important? Why should we get excited about them?
They are fundamental components in many of our current high-value technologies.
Mm-hmm.
Electronics, catalysts, magnets for wind turbines, batteries. The list is extensive.
Right. So connecting this to the bigger picture, space mining isn't about, shutting down mines on Earth tomorrow.
That is not the projection. It represents an expansion, a diversification, a new tier of industrial activity operating in orbit and eventually across the solar system.
So diversifying our resource portfolio, that sounds crucial for, long-term sustainability and growth.
Precisely. It reduces single-point dependency and opens new economic frontiers.
Okay, so the moon seems like the first stop, the most immediate target. But are there arguments for maybe prioritizing asteroids in the longer run, given that potential value you mentioned?
An interesting strategic question. The moon offers crucial advantages: proximity, lower gravity assist for processing and launch, and that readily accessible water ice for fuel and life support. It is the logical proving ground.
Right, the ground zero, as some of the info called it.
However, asteroids, particularly near-Earth objects or NEOs, theoretically hold concentrated deposits of high-value platinum group metals and other industrial materials that may be less abundant or harder to extract on the moon.
So moon first for learning and infrastructure, asteroids later for the big industrial payoff.
That appears to be the emerging consensus trajectory, yes. Develop ISRU capabilities on the moon, then apply them to asteroidal targets.
And speaking of the moon as ground zero, it's relatively close, right? Accessible with tech we basically have or are refining.
Its gravitational well is significant but manageable compared to Earth, aiding both landing and launching processed materials.
And NASA's Artemis program fits right into this, doesn't it? Aiming to build up infrastructure near the lunar South Pole.
Precisely where the persistent shadows harbor significant water ice deposits.
And there's also the ESA's Moon Village concept, that international idea for shared lunar facilities. Cooperation seems key here.
Collaboration will likely accelerate development and distribute costs and risks.
That NASA Psyche mission, I know it's for science, not mining, but it really highlights the potential, right? This one asteroid, mostly nickel and iron.
Believed to be the exposed core of a protoplanet, yes, with significant trace amounts of gold and platinum.
And the estimates are potentially more precious metal than humans have mined in our entire history on one asteroid. That's just staggering.
The scale is difficult to comprehend in terrestrial terms.
What are the biggest hurdles, then, to actually tapping into something like that? It seems way harder than the moon.
Significant challenges remain. Rendezvous and docking anchoring with low gravity, potentially rotating bodies, developing autonomous mining robotics hardy enough for the space environment, power generation, and crucially, the economics of retrieval or in-space processing.
But the groundwork. You mentioned companies like Planetary Resources and Deep Space Industries. Even though they got acquired, they started this ball rolling.
Correct. Their pioneering work on prospecting techniques, small-scale robotic extraction concepts, and even preliminary studies on off-world smelting laid vital theoretical and engineering foundations.
And the timeline, some sources suggest, like 10 to 15 years for asteroid materials to start fueling orbital factories.
Contingent on continued investment, technological breakthroughs, and favorable market conditions.
But if the tech is still mostly developmental, how realistic is that time frame?
It reflects the rapid acceleration curve often seen in disruptive technology sectors, coupled with significant venture capital and government interest. The trajectory is clear, even if the exact timeline has uncertainties.
Okay, so let's say we're getting this stuff ice from the moon, metals from asteroids. Then what? Like you said, beaming it all back to Earth isn't always the main goal or even efficient for many things.
Precisely. The information we analyzed outlines 4 key elements needed for this infrastructure. First, mobility.
Getting materials from A to B in space?
Yes. Autonomous rovers on surfaces, surface-to-orbit launchers, perhaps electromagnetic or utilizing ISRU propellants and orbital transfer vehicles or tugs, to move refined materials between locations, like lunar orbit and Earth orbit.
Okay, mobility. What's next?
Processing and refining, creating value close to the source. On the moon, this means electrolysis plants for fuel production.
Splitting that water ice.
Yes. Also, systems for extracting metals from regolith, 3D printing with processed regolith, potentially solar-powered smelters. Automation is critical here.
Got it. Mobility processing, then.
Storage and distribution. This is vital, especially for commodities like lunar-derived propellant.
Fuel depots in space.
Exactly. Cryogenic fuel depots in lunar orbit, perhaps on the surface, and potentially Lagrange points, fed by ISRU production to dramatically lower the cost of in-space transportation. Think of it as creating interplanetary gas stations.
Wow. Okay, and the fourth element?
Construction and manufacturing. Directly in space, using these processed resources.
This is the really mind-blowing part. Like 3D printing habitats from moon dust, building solar panels using lunar silicon.
Making spare parts on demand for spacecraft or lunar bases, additive manufacturing, robotic assembly, leveraging the unique environment of space, like microgravity, for novel production techniques.
That capability? It changes the entire game.
Fundamentally, when these 4 elements, mobility, processing, storage, and construction, become integrated, you transition towards a self-sustaining, or at least partially self-sustaining, space economy.
Lunar outposts become more than just flags and footprints. They become hubs.
Hubs supporting orbital manufacturing, staging points for deep space missions, propellant suppliers, asteroid shift from scientific targets to potentially valuable resource nodes integrated into this network.
And the key takeaway seems to be, these resources only really unlock their true value when they're part of this functioning system, not just stuff we have to haul back to Earth constantly.
Precisely. Independence from constant, costly Earth resupply is the strategic objective.
And this isn't just, theoretical anymore, is it? There's real economic and policy stuff happening.
Correct. Space agencies globally are investing significantly in ISRU research and technology demonstration missions.
And laws are being passed, like in the US and Luxembourg, recognizing rights to resources extracted in space.
Establishing legal frameworks is crucial for attracting private investment, and the market projections, while speculative, indicate a multi-billion, potentially trillion-dollar industry in the coming decades.
That signals a huge shift, right? We're moving beyond just launching things.
Resource strategy is emerging as the next major domain of space activity, fostering both competition and potential cooperation.
And for marketers, like us, the opportunity isn't just selling rocks, is it?
Far from it. It is about crafting the narrative of humanity becoming a multiplanetary species. It's about the enabling power of these resources.
Built with space materials. Imagine that tagline. Highlighting maybe the clean sourcing, the rarity.
Or the ultimate origin story. There's also a powerful sustainability message. Utilizing space resources could potentially alleviate some environmental pressures on Earth.
Yeah, that's a huge angle. Plus, just the inspiration factor, STEM education, getting kids excited about this incredible technology.
Ultimately, as the analysis suggests, the marketing challenge and opportunity is profound. We're not merely selling minerals.
Or marketing, survival, expansion, the future, basically.
Making the invisible visible. Demonstrating how lunar ice enables a journey to Mars. How asteroidal metals construct the orbital platforms of tomorrow, humanizing the technology.
And telling that story of independence, the self-sufficiency that off-world resources can unlock.
That is the core narrative potential.
So what does this all mean for you, listening? It means the future isn't just up there somewhere. It's actively being built, piece by piece, resource by resource.
The process has begun.
Absolutely. And if this deep dive into the incredible potential of off-world resources sparked your curiosity, be sure to like and subscribe to Astra, the Exo Marketing Podcast. We'll have plenty more explorations into the future of space business.
Your continued engagement is registered and appreciated.
Join us next time as we continue to look beyond our world. Until then.
The cosmos is calling. Let's build its future, one resource at a time.